Let's look at an example now that relates to the circular motion of the Earth. We all know that our Earth rotates about its axis and it rotates about the Sun. We'll focus on the actual rotation. If the acceleration at the equator is greater than the gravitational acceleration g, objects would actually fly off the Earth's surface and into space. So it's a hypothetical situation. And the question here is, what would the period of the Earth's rotation have to be for this to occur? Here's the Earth with the axis of rotation about which the Earth rotates. And here I have marked the equator of the Earth, which is the largest circle here with the radius r. We know that for circular motion, the acceleration is centripetal acceleration and has to be equal to v squared over r. The problem tells us that if this acceleration should exceed g, which is 9.8 meters per second squared, things on the equator will actually fly off into space. On the other hand, we know that velocity or speed for a uniform circular motion is going to be equal to distance over time. Now, technically, the Earth has some irregularities, but for the purpose of this problem, we can totally neglect any variations in the speed of the Earth as it rotates about its axis. So we're going to consider this motion more or less a uniform motion. For one revolution, remember, this formula just simply looked like 2 pi r, the circumference over the time for one revolution, which we called the period. For the equator, the largest circle here that we can see on Earth as everybody rotates together, the radius of the equator is going to be simply the radius of the Earth. Remember, the radius of the Earth is a constant. You can look it up very quickly on the internet, and it's 6.38 10 to the 6 meters. I've given the value here in meters because those are our standard metric units. With that, we can see that the period of rotation depends on the radius and the speed. And in fact is equal to 2 pi r, the radius of the Earth, divided by the speed of a point on the equator of the Earth. That speed, of course, is related to the acceleration. We have the acceleration being equal to v squared over r. Remember, for the equator, that r is going to be simply equal to the radius of the Earth. That gives me that the speed with which the objects are moving on the equator around the axis of rotation is equal to square root of the acceleration, the centripetal acceleration, times the radius of the Earth. And here is the solution to the problem, really, because if I take this formula here and combine it with the formula with the relationship that I found between the period and the speed, I can determine what the period is if the centripetal acceleration should exceed g, or be equal, in the limiting case, be equal to g, 9.8 meters per second squared. So to that end, let's take the formula for the velocity, for the speed, square root of a times the radius of the Earth, and see what that speed should be. Square root of 9.8 times 6.38 10 to the 6. I omitted the units here for brevity, but that gives me for the value of the speed to be 7.9072 10 to the 3 meters per second. Notice here I'm carrying on extra digits, significant digits. This is not the answer, the end of my problem, and I don't want to accumulate round-off errors. So with that value for the speed, I'm ready to go back to the formula for the period here and substitute. So I'm going to have 2 pi, the radius of the Earth, 6.38 10 to the 6, divided by the value for the speed, which I already determined, 7.9072 10 to the 3 meters per second, which gives me for the period of rotation, for that hypothetical situation, to be 5.07 10 to the 3 seconds. Here I have rounded down to the 3 significant digits, which is usually acceptable as a final answer. If you're like me and you don't want to put the numeric values until the very end, here's how you can actually work out things symbolically. When you use the formula for the period, 2 pi r over v, you're going to replace v here with its own expression. So you're going to have, for the period of the Earth, the hypothetical period of the Earth, 2 pi radius of the Earth divided by square root of the centripetal acceleration a times the radius of the Earth. Of course, noticing that the radius of the Earth here appears both in the numerator and denominator, you can write this expression as 2 pi square root of the radius of the Earth divided by the square root of the centripetal acceleration. And this is where I personally would put the numeric values, but this is really for me, for my own purpose. Otherwise, you're welcome just to start putting the numbers early and get some sense for what is happening and how much the velocity is. So here I have substituted 6.38 10 to the 6 meters for the radius of the Earth, and 9.8 meters per second squared for the value of the acceleration. And once again, I get for the period 5.07 10 to the 3 seconds, which, by the way, is about 84.45 minutes. I kept an extra digit here. I am always reluctant to round if the last digit happens to be a 4 or 5. They just seem to be too much in the middle between two numbers for rounding purposes.